In this section, I'm going to discuss the computation of the inverse Laplace transform. Recall from earlier that the inverse Laplace transform little x of the function big X is given by this particular formula here, where the real part of s equals sigma is contained in the region of convergence of big X. Unfortunately, this formula for little x involves a contour integration, which can often be somewhat tedious to compute. For this reason, we don't typically find the inverse Laplace transform directly using this formula. For rational functions, the inverse Laplace transform can be more easily determined using partial fraction expansions. Using a partial fraction expansion, we can express a rational function as the sum of lower order rational functions, whose inverse Laplace transforms can then typically be found in tables. At this point, I'd like to consider a couple of examples of finding inverse Laplace transforms of functions. First, I'd like to consider example 7.27. In this example, we're asked to find the inverse Laplace transform little x of the function big X, where big X is given by this particular formula here. The general approach to be taken in the solution to this example is to use a partial fraction expansion of big X. So first we need to identify the form of this partial fraction expansion. To do this, we need to determine the poles of big X and their orders. So we proceed to fully factor the denominator in the expression for big X, in other words, this denominator here. This yields the factorization shown on this line. From this factorization, we can see that big X has two poles. It has a first order pole at -1, coming from this factor s plus 1, and it has a first order pole at 2, coming from this factor s minus 2. So since there's two first order poles, the partial fraction expansion of big X will have two terms. The first term here comes from the pole at -1, where we have the coefficient a1 to be determined, and the second term here comes from the pole at 2, with this coefficient a2 to be determined. Now we proceed to find the coefficients of the partial fraction expansion. First, we find the coefficient a1. Since a1 is associated with the first order pole, the formula that we use to compute a1 is the formula for partial fraction expansion coefficients associated with simple poles. So this is the formula that's being used on the right-hand side here. We're simply taking the function that we're trying to find the partial fraction expansion of, which is x. We multiply it by the factor that's associated with the coefficient a1, which in this case is the factor s plus 1, and then we evaluate this expression at the value of s that forces this factor to go to 0, which will be s equal to -1. And if we grind through the arithmetic, the value that we get is minus 2/3. Then we proceed to compute the coefficient a2, in other words this coefficient here. This coefficient is associated with the first order pole. So when we compute a2, we're going to use the formula for a partial fraction expansion coefficient for a simple pole. So what this formula says is we take the function that we're trying to find the partial fraction expansion of, which is x. We multiply it by the factor associated with the coefficient we're trying to compute, which is the factor s minus 2. And then we evaluate this expression at the value of s that forces this factor to go to 0, which will be s equal to 2. And if we grind through the arithmetic here, the value that we get is 2/3. Next, we can take the two coefficient values a1 and a2 that we've computed and substitute them into this equation to obtain our partial fraction expansion for big X. This yields this line here. At this point, I need to pause in order to scroll the example upwards so that we can see the remainder of the solution. Now that we have the partial fraction expansion of big X, we can proceed to take the inverse Laplace transform of big X. And using the linearity property of the Laplace transform, we can trivially obtain this next line here, where we now have two inverse Laplace transforms we need to calculate. The inverse Laplace transform of 1 over s minus 2 and the inverse Laplace transform of 1 over s plus 1. At this point, we need to remember that the region of convergence is a fundamental part of the specification of a Laplace transform. So when we compute the inverse Laplace transform of a function, not only do we need to know the algebraic expression for the function, but we must also know its region of convergence. So what region of convergence should we use for 1 over s minus 2 when we compute this inverse Laplace transform here? And what region of convergence should we use for 1 over s plus 1 when we compute this inverse Laplace transform here? This is the issue that I want to address next. So the answer to this question lies on the previous line, in other words, this line here. In the original problem statement, we were told that the function big X converges in this region in the annotation, in other words, real part of s between minus 1 and 2. Because the left-hand side of this equation is equal to the right-hand side of this equation, this implies that the right-hand side also must converge for the region that's written in this annotation. Furthermore, in order for this right-hand side to converge in this region written in the annotation, this means that each of the individual terms must converge in this region. So this first term here must converge in this region here, and this second term also must converge in this region here in the annotation. In other words, we have to choose a region of convergence for 1 over s minus 2 such that it converges in this region real part of s between minus 1 and 2. Similarly, when we choose the region of convergence for 1 over s plus 1, we have to choose a region of convergence that includes this region real part of s between minus 1 and 2. So keep this in mind because we're going to need this when we go forward later in the solution. So let's consider now the inverse Laplace transform of 1 over s minus 2. So this is this function written down here in the annotation. This is a rational function with a single pole at 2. So we have a pole at 2. And even before we go to our table of Laplace transform pairs, we know that this function has two possible regions of convergence. In other words, there will be two entries in our table that we can choose from. One which will correspond to a region of convergence which is a left half plane that converges to the left of the pole, which is this green region here. And the other entry in our table will correspond to a right half plane region of convergence which converges to the right of this pole, in other words, this purplish region here. And we have to choose between them. Now, if you recall from earlier, we said that the region, whatever region we choose, must include this region here, the real part of s is between minus 1 and 2. In other words, the region that's marked here, real part of s between minus 1 and 2, is the region sort of between these arrows here. So this area that lies in the green region. So when we're choosing the region of convergence for 1 over s minus 2, we need to choose this green region here, this left half plane region of convergence, which is the region of convergence real part of s is less than 2. So using our table with this particular region of convergence, we end up with this particular inverse Laplace transform. Now we proceed on to take the inverse Laplace transform of 1 over s plus 1. So here we have 1 over s plus 1. This is a rational function. This is a function with a single pole at minus 1. So even before we go to our table of Laplace transform pairs, we know that there's going to be two entries that we need to choose between. One of them will correspond to a left half plane region of convergence, in other words, this green region here. The other will correspond to this right half plane region of convergence, which is this purplish region here. So which one do we choose? Well, again, we need to choose the one that has the real part of s between minus 1 and 2 contained in its region of convergence. In other words, this region that's marked by the double arrow here. This corresponds to the area that falls in this purplish region. So in this case, we need to choose a right half plane region of convergence for the rational function 1 over s plus 1. In other words, we need to choose this particular region of convergence here that I've highlighted. And if we do this and we use our table, we get this particular inverse Laplace transform here. So now that we've computed each of these inverse Laplace transforms, this one here and this one here, we can now substitute these results. And when we do this, this gives us this next line here, which can be very easily manipulated into the form of this last line, which is our final answer. Next, I'd like to consider example 7.28. In this example, we're asked to find the inverse Laplace transform little x of the function big X, where big X is given by this formula here. The general approach to be taken in the solution to this example is to use a partial fraction expansion of big X. So first we need to identify the form of this partial fraction expansion. The form of the partial fraction expansion of big X is determined by the poles of big X and their orders. From the factorization of big X shown here, we can see that big X has a second order pole at -1 coming from this s plus 1 squared factor, and a pole at -2, which is first order, coming from this s plus 2 factor. So given these poles, the partial fraction expansion of big X will have the form that's shown here. We'll have two terms that are coming from the pole at -1, which is second order, and one term coming from the pole at -2, which is first order. And then we need to determine these coefficients a11, a12, and a21. So to calculate these coefficients, we use the formulas for computing partial fraction expansion coefficients. And for the first two coefficients, a11 and a12, since these coefficients are associated with a repeated pole, we have to use the formula for the repeated pole case, which is what's being substituted into here on this line, and also here on this line. And I've color-coded things to show where we're substituting different quantities into these formulas. This purplish color is showing where we're substituting the coefficient index into this formula here, and the green color is showing where we're substituting the order of the pole into this formula here, and similar for this formula down below. In the case of a21, since this corresponds to a simple pole, in other words a first order pole, we use the formula for the simple pole case, which is a much simpler formula, which is what's being substituted into here. And when all is said and done, for a11 we get a value of 3, for a12 we get a value of -1, and for a21 we get a value of -3. If we substitute these coefficients into this formula here, this gives us this line below. So here is our partial fraction expansion of big X. At this point, I'm going to pause in order to scroll the example upwards so that we can see the next part of the solution. Now we continue from where we left off previously. We had just found the partial fraction expansion of big X, which is given here. Taking the inverse Laplace transform of this equation with the help of the linearity property of the Laplace transform, we obtain this equation here, equation 7.7. In this equation we have three inverse Laplace transforms to compute. The inverse Laplace transform of 1 over s plus 1, 1 over s plus 1 squared, and 1 over s plus 2. At this point, we need to remember that the region of convergence is a fundamental part of the specification of a Laplace transform. So when we compute the inverse Laplace transform of a function, not only do we need to know the algebraic expression for the function, but we must also know its region of convergence. Therefore, we need to determine the region of convergence to be used for each of these functions whose inverse Laplace transform is to be taken. In other words, when we take this inverse Laplace transform here, what region of convergence do we use for 1 over s plus 1? And when we take this inverse Laplace transform here, what region of convergence do we use for 1 over s plus 1 squared? And when we take this inverse Laplace transform here, what region of convergence do we use for 1 over s plus 2? This is what we need to consider next. The answer as to what regions of convergence should be used lies in the preceding equation, in other words this equation here, which has the partial fraction expansion for big X. In the original problem statement, we're told that big X has the region of convergence in the annotation here. In other words, the real part of s is greater than -1. Because the right-hand side of this equation is equal to the left-hand side of this equation, the right-hand side of this equation must also converge for the real part of s is greater than -1. Furthermore, in order for the right-hand side of this equation to converge for the real part of s is greater than -1, each of the individual terms on the right-hand side must converge for this region. In other words, this first term here must converge for a real part of s is greater than -1. The second term must also converge for the real part of s is greater than -1. And the last term also must converge for real part of s is greater than minus 1. So we'll keep this in mind as we go forward, because this particular result is going to be important later. Now let's consider each of the inverse Laplace transforms in equation 7.7. First, let's consider the inverse Laplace transform of 1 over s plus 1. 1 over s plus 1 is a rational function with a single pole at minus 1, which is this pole shown here. This particular function can converge either to the left of the pole, in other words this purple shaded region here, which is a left half plane, or the function can converge to the right of this pole, in other words in this green shaded region, which corresponds to a right half plane. So when we go to our table of Laplace transforms to look up the inverse Laplace transform of 1 over s plus 1, there's going to be two relevant entries in our table, one which corresponds to this left half plane region of convergence, and one which corresponds to this right half plane region of convergence. So we have to decide which one we should select. So now recall from earlier, we said that the region of convergence must include the real part of s is greater than minus 1. So here the region real part of s is greater than minus 1 is contained in this green region, in other words in this right half plane. So when we're taking the inverse Laplace transform of 1 over s plus 1, we want to choose the region of convergence for it to be this right half plane. In other words, the real part of s is greater than minus 1. Now let's consider the inverse Laplace transform of 1 over s plus 1 squared. 1 over s plus 1 squared is a rational function with a second order pole at minus 1, which corresponds to this pole here. And this particular function can converge either to the left of the pole in this purple region, which is a left half plane, or it can converge to the right of the pole in this green shaded region, which corresponds to a right half plane. So even before we go to our table of Laplace transform pairs, in order to look up the inverse Laplace transform of 1 over s plus 1 squared, we know that there's going to be two relevant entries in our table, one which corresponds to this left half plane region of convergence, and one which corresponds to this right half plane region of convergence. And we're going to have to choose between these two entries in the table. As we saw earlier, the region of convergence that we choose must include the real part of s is greater than minus 1. And the real part of s is greater than minus 1 is essentially this region here, which falls in the green region. In other words, it falls in the right half plane region of convergence. Therefore, when we're choosing the inverse Laplace transform using our table, we have to choose the region of convergence for 1 over s plus 1 squared to be this right half plane region of convergence in green. In other words, we need to choose the region of convergence to be the real part of s is greater than minus 1. Lastly, let's consider the inverse Laplace transform of 1 over s plus 2. 1 over s plus 2 is a rational function. It has a single pole at minus 2, which is this pole here. Therefore, the function can converge to the left of the pole in this purple shaded region, which is a left half plane, or it can converge to the right of the pole in this green shaded region, which is a right half plane. So when we go to our table of Laplace transform pairs to look up the inverse Laplace transform of 1 over s plus 2, there will be two relevant entries in our table, one that corresponds to this left half plane region of convergence, and one that corresponds to this right half plane region of convergence. If you recall from earlier, however, we said that the region that we choose must include the real part of s is greater than minus 1. So of these two regions, this left half plane and this right half plane, the one that includes the region real part of s is greater than minus 1 is the right half plane, in other words this green shaded region. Therefore the region of convergence for 1 over s plus 2 that we need to choose is to the right of this pole at minus 2. In other words, we need to choose the region of convergence real part of s is greater than minus 2. At this point I'm going to pause in order to flip to the next page of the example so that we can see the remainder of the solution. For convenience, I've included equation 7.7 from the previous page in the annotation at the top of this page. Now that we've identified all of the necessary regions of convergence to use for the inverse Laplace transforms in equation 7.7, we can proceed to look up each inverse Laplace transform in our table of Laplace transform pairs. This yields the three inverse Laplace transforms shown here, which are numbered 1 through 3. Substituting these three inverse Laplace transforms into equation 7.7 yields our final answer, which is this answer here. In other words, we have the inverse Laplace transform little x of the function big X.